lecture number 9 of HVDC transformer system. In this lecture, we learn about the power flow in HVDC lines. So, as you know, the HVDC system consists of a rectifier station, the DC transmission line, and the inverter station. AC power is first converted by the rectifier and transported by the DC line and or cable. After that, it is inverted by the second converter into AC at the other terminal. Any converter can either as a rectifier or a inverter with the proper control so that the power flow in either direction. The power flow and the current through an HVDC line can be controlled by either controlling the DC voltage or the inverter end or a rectifier. So the current through the DC line, it is given as the ID. It is a DC current is equal to VD1 minus VD2 divided by R. Where VD1 it is a DC voltage on the rectifier, VD2 it is a DC voltage on the inverter end, and R it is a resistance of the DC line per pole. Also, you can calculate the DC voltage in the middle of the DC line. It is denoted by VD3 is equal to VD1 plus VD2 divided by 2. So the DC power through the line, we know what is the power. DC power equation is P equal to VI. So similarly, the DC power through the line, it is called the PDC is equal to VDI. So the value of VD1 and VD2, it is changed in two ways with the use of step changing controller, which is slow and take 8 to 10 seconds. The another option is the fast variation of DC voltage can be achieved through the gate control by varying the delay angle for a few milliseconds. You can control the voltage. The value of PDC can be controlled quickly because of a small value of R. Here the value of R is very small. On the DC side voltages, VD1 and VD2 at both ends of the DC line have definite relations to the corresponding the AC voltages, which is depend upon the position of tape changing transformer or the delay angle of the converter. So we usually take the VD2 is held at a certain value by voltage control of the inverter terminal, and the current ID is controlled by the rectifier terminal. So the current through the rectifier and the inverter must be the same, and therefore we can write the value of ID1 is equal to ID2 is equal to ID, where ID1 is a rectifier current, ID2 is your inverter current. So the power at the rectifier end, it is calculated, it is denoted by PD1 is equal to PD1 into ID. Now as you know, what is the value of ID? It is VD1 minus VD2 divided by R. So we put the value of ID in this equation, we can get VD1 minus VD2 divided by R. So the power at the rectifier terminal, it is denoted by PD1 is equal to VD1 square divided by R minus VD1 VD2 divided by R. This is the power at the rectifier terminal. And it can be controlled by controlling the difference of voltage VD1 and VD2 by holding VD1 at a fixed value. Right? So the power at the rectifier end, we can control it with the help of this difference. Similarly, we can calculate the power at the inverter end, which is called the PD2, is equal to VD2 into ID. Again, put the value of ID, it is VD1 minus VD2 divided by R. So you can get the power is minus VD2 square divided by R plus VD1 VD2 divided by R. Now here it is a minus sign. The negative sign of the first term indicates that power is received by the inverter. Remember these things. So this is your power at the inverter end. It is PD2 is equal to minus VD2 square. Here it is square. Now we can calculate the losses in the DC system. So the losses is called the P loss, which is denoted by PL is equal to PD1 minus PD2, which is equal to PD1 ID minus PD2 ID. If we take the ID as a common, we get the equation VD1 minus VD2 into ID. Again put the value of ID, which is VD1 minus VD2 by R. So VD1 minus VD2 is in the same. Value of ID is VD1 minus VD2 divided by R. So if we simplify this, we can get the power loss PL is equal to VD1 minus VD2 whole square divided by R, which is equal to ID square. So the DC line loss increase with the DC power. Now we can calculate the power in the middle of the DC line, which is denoted by the PDM. Power in the middle of the DC line, which is denoted by PDM, is equal to PD1 plus PD2 divided by 2. So put the value of PD1 and PD2. So this remains the same, 1 by 2 is same. The value of PD1 is PD1 square divided by 2 minus PD1 PD2 by R. Sorry, it is not a 2. The first term is VD1 square divided by R. Now value of VD2, it is minus VD2 square divided by R plus VD1 VD2 divided by R. So if we simplify this equation, you will get VD1 square minus VD2 divided by 2. But this is your power at the middle of the DC line. Remember this. It's VD1 square minus VD2 square divided by 2R. So the power at the rectifier end can be other terms in terms of middle of the line. It is expressed as the PD1 is equal to the power at the middle of the line plus half losses. This is for a rectifier end. Similarly, we can write the power at the inverter end in terms of PDM. This PDM minus half losses. So based on that, we can now solve some example based on this theory or equations. First example, based on this, a bipolar two-terminal HVDC link, uh, bipolar two-terminal HVDC link is delivering 1000 megawatt, 1000 megawatt at plus or minus 500 kV at the receiving end. At the receiving, the total losses, the total losses in the DC circuit, in the DC circuit are 50 megawatt. Calculate the following. The first part is sending end power. Sending end power. The second part is sending end voltage. The third part is power in the middle of the line. Power in the middle of the line. The fourth part is the voltage in the middle of the line. Voltage in the middle of the line. And last one is the fifth one is the total resistance of DC circuit. Total resistance of the DC circuit. So the bipolar two-terminal HVDC link is delivering 100 megawatt at plus or minus 500 kV at the receiving end. The total losses in the DC circuit are 50 megawatt. Calculate the sending end power, sending end voltage, power in the middle of the line, voltage in the middle of the line, and the total resistance of the DC circuit. How can we start? The sending end power, right? So the receiving end power is given and the losses is given. So you can easily calculate the sending end power, the first part, the sending end power is equal to the receiving end power plus losses. So you know the value of receiving end power is 1000 megawatt. And the losses is 50 megawatt. So you can calculate that sending end power is 0.5. megawatt. The second part is the sending in voltage. It is denoted by sending in, this is a rectifier side. So it is denoted by VD1 is equal to PD1 divided by ID. So you know the value of PD1 is sending in power. This one is a 1050 megawatt. But the current, the DC current is unknown. So you can calculate the DC current is equal to the power is given, receiving power is given. It is 1000 megawatt, so 1000 into 10 to 6, and it is a bipolar link. So you have two terminals. So this is 2 multiplied. The rating of that is 500 kV. So you can use by 2 into 500 minus 3. So you can calculate, you get the value of DC current, which is 1000 ampere. So by putting the value of DC current and the sending in power, you can calculate the sending in voltage, which is VD1 is equal to the sending in power is 1050 megawatt. So 1050 into 10 to 6 divided by the current is 1000. So you will get the value of voltage, it is 1050 kV. This is your sending in voltage. So this is a bipolar link. So the voltage between the poles, it is divided by 2. So you can write here the between the pole it is plus or minus 5 to 5 kV per pole. Now the third part, it is a power in the middle of the line. So it is mm, the power in the middle of the line. It is equal to the power at the receiving end, power at the receiving end plus half losses. If you take the power at the sending end, then it is minus half losses. So it is 1000 plus the losses is 50 megawatt. So it is divided by 2. So it is 25. So you can get the power in the middle of the line. It is 1025 megawatt. The next parameter is the voltage in the middle of the line. Fourth one, voltage in the middle of the line. So it is the power in the middle of the line divided by ID. So it is called the power in the middle of the line divided by ID. What is the power in the middle of the line? It is 1025 megawatt. So it is 1025 multiplied by 6. What is the value of DC current? It is 1000 ampere. So you will get the voltage in the middle of the line. It is 1025 kV. And again, this is a bipolar link. So the voltage in the middle of the line, it is also we write VDM is equal to plus or minus 512.5 kV. And the last one, it is the total resistance of the DC circuit. The fifth one, total resistance of the DC circuit. So you know the equation of losses PL is equal to ID square R. So you know the value of PL, it is 50 megawatt. You know the value of current, it is ID, it is 1000 ampere. So you can easily calculate the volt resistance R. So your equation becomes R is equal to PL upon ID square. So PL it is 50 megawatt. So 50 divided by 6 ID square it is 1000 square. So your resistance is 50 ohm. So by this way you can solve the example of power flow in a HVDC transmission system. Thank you.